All right. Thank you very much, Silke, and thank you very much for the invitation and for having me today. It's really a pleasure to come and talk to the QSimF people. I'm going to talk about quasi-normal modes, which is a topic which I'm very new to, and I know that some people among you are much more experienced with them. And my hope is that I give you some idea about what we've done here at Laboratoire Kastler Brossel, and then we can chat. And we can chat about what we are seeing may actually mean. Okay, so off I go. So this work I've done mostly with Jacopo Carusotto and Luca Giacomelli, who was doing his postdoc with Jacopo until a few months ago, and who is now in Paris in another group. And also with the students Malo Joly and Quentin Valnet, and some other people from the quantum optics group at Laboratoire Kastler Brossel. So all the very nice things that I will say go to them, and all the mistakes solely go to me. Okay, so the plan of the talk today is that I just tell you a little bit about what I understand as being the Hawking effect, how we can create effective spacetimes, and then I want to tell you about this platform in which I study the effect, which is polaritons. And then I will tell you how we do an analog with polaritons, and what is special about this analog, which is that it's out of thermal equilibrium. And we will see how that has enabled us to see this excitation of the QNMs, quasi-normal modes. All right, so the Hawking effect. So by the Hawking effect, I really mean the thermal emission of radiation from black holes. And in general, I mean the vacuum fluctuation excitation of the horizon. And so this all happens because this all happens on black holes. So we have here a space-time diagram with space running horizontally and time running upwards. And we look at the history of modes coming from minus infinity to plus infinity, incoming into outgoing modes, as they travel through a shell of collapsing matter. And as they travel through the shell of collapsing matter, the in modes and the out modes are not exactly the same. And this is because intuitively what we can do is, in expressing the out modes in terms of the in modes, we can see that the in modes, as they travel through the collapsing shell, they will blue shift, and the out modes, they will red shift. And simply because the curvature has changed through time, as the out modes exit, the red shift will largely exceed the blue shift, and the in and out modes will not have the same vector basis, and therefore we will have a mixing of positive and negative frequency waves, or of annihilation and creation operators of the field, providing that this beta coefficient I have written here is non-trivial. And because of that, basically the in and out vacua are not the same, and we have Hawking radiation. So the out modes are populated with some amount of emission, or particles, as some people like to say it. For black holes, it's very well known that the problem with this is that the redshift is very, very large, meaning that the surface gravity of the black hole gives us incredible frequencies in the e to the 50 for the in modes. E to the 50, I don't know what, and it doesn't matter because e to the 50 is so large that I don't really need to give a unit to this. But we have a Trans-Planckian problem, and that's not at all what I want to talk about today, but it exists, it's out there, and people are thinking about it. And it may have to do with some microphysics near the horizon. Now, the thing is that even with this e to the 50 in frequencies and so on, the outflux of Hawking radiation is very, very small, so it cannot really be seen from actual black holes. And that led Unruh to ask himself whether it was possible to see it in other conditions for other regimes of space-time curvature, and to invent analog gravity in doing so. And that's precisely what the talk today is about. It's about analog gravity. So it's about this idea that we can think of the curvature of space-time as an effective geometry for the waves that propagate on it. And so, for example, if we think about the Schwarzschild black hole, so it's a stationary static black hole, we can write its we can write it in the Panevet-Gullstrand coordinates, and there we have space that seems to flow at an increasing speed across the horizon, where it exceeds the speed of light, up to infinity at the singularity. And the very famous way in which Bill explains that to all of us was this story of the waterfall, with an increasing speed of a waterfall in which fish would be swimming and emitting waves. And as the fish go closer to the waterfall, they would get dragged by the speed of the waterfall. There is a point at which the speed of the flow exceeds the speed of the fish, and that's the event horizon for the fish. And from there on, also the sound waves that would be emitted by the fish would be infinitely redshifted, such that they cannot come out of that region. And so this surface at which the flow velocity of the water exceeds that of the fish would be the analog of an event horizon. And of course, we are not doing anything with fish, as you know. We are doing all of this with sound. And in this PRL in 1981, Bill showed that well, the wave equation for sound in a superfluid could be cast into the exact same way as the wave equation for a massless scalar field on the Schwarzschild spacetime, for example. This was later generalized to other spacetimes by Matt Visser. And so, well, waves in the lab may be made to behave really as though they were on an effective curved spacetime. And if that's the case, then quantizing the waves give us Hawking radiation. That's also shown in the 1981 paper. And there are many experiments in which this has been seen now. So these are all experiments done in one-dimensional configurations. The bottom two in surface waves in water and phonons in an atomic VEC were done with the waterfall configuration, so an increasing speed of a flow. Whereas there is also some possibilities to do it with nonlinear optics, and Frieder, who is attending the talk, can tell you much more than me about this. Okay, and what's interesting here is that basically we have this waterfall configuration that allows us to create an effective horizon for the waves. And quantum fluids, like atomic Bose-Einstein condensates, can do that. And besides that, we have many other possibilities. We can use many other systems, and we can simulate also many other systems. So that gives us this means to model the field phenomena, or in the way in which I've learned that we have to say it, we are doing analog quantum simulation of field phenomena. So what I want to tell you about today is really exactly this. And I want to tell you how we do it with polaritons. So polaritons are a quantum fluid, very much like the ultra-cold atomic condensates of atoms, of rubidium or of lithium, for example, or just like liquid helium. Polaritons can be made to condensate, or they can be made to be superfluid. And they are called quantum fluids of light. And for most people, this is not a very well-known thing, because they picture light as photons in vacuum, sort of, and these photons are massless, so they cannot have a kinetic energy, and they do not interact with one another. In order to have a quantum fluid of light that will have superfluid behavior or will condensate, we need to engineer an effective mass for the kinetic energy and some means for interactions from one photon to another. And at Laboratoire Kastler Brossel, we do this in two ways. We have one way in which we have very conservative dynamics. We send a laser beam through a cell of hot rubidium atoms. And this is a Kerr medium, so we have interactions and mass that way. But the way I want to tell you about today is the one that's on the right of the screen. It's the cavity geometry, where we trap the photons inside a cavity and have them interact with the excitons of a semiconductor, and that gives them an effective mass and interactions, respectively. And what's interesting is that the dynamics of this system are out of equilibrium. So let's dig into that. Here is the system we consider. We have our microcavity. So the sample is basically two sets of distributed Bragg mirrors. So these are very highly reflective mirrors with a very high finesse of the quality, of the order of 10,000 or so. They are facing each other. If I send a photon through the back of one of those mirrors, it will bounce back and forth in between the mirrors for a very large number of times. But after some time, it will exit the cavity, and I will be able to detect it with a camera. A photon that is trapped inside of a mirror, inside two mirrors, inside a cavity, sees its dispersion relation go from being totally linear as a function. So this is the frequency as a function of the wave number of the light. And we see that the dispersion is not linear. It's got this parabolic shape here. This parabolic shape is associated with a massive field. So inside the cavity, the photon has an effective mass. That's just confinement. And then inside the cavity, we also have an extra layer of semiconductor, which is a quantum well. And so the quantum well is basically just a semiconductor in which we send a photon, and that very easily separates an electron from an exciton. So the photon gets dressed by this so-called exciton. And the exciton, just like the photon, has a parabolic dispersion. However, it's extremely massive. It's got the mass of the electron. So at the scales at which I'm plotting the wave number here on the right-hand side, this looks like it's flat, but it's just a very large parabola. So in coupling with the excitons, with the quantum well excitons, the photons will be able to interact. This is done by strong coupling, and this is only possible provided that the Rabi splitting of my cavity exceeds the lifetime of the excitons and of the photons. So for the photons, that's easy. It's just about the quality factor. For the excitons, it means that we have to cool the system to cryogenic temperatures, about 12 kelvins and less. So we have strong coupling, and upon strong coupling between the photons in blue and the excitons in red, we see two new eigenstates of the system that appear: the upper polariton at high frequencies and the lower polaritons at low frequencies. Because of some thermodynamic arguments, all the dynamics that we are interested in are all happening in the lower polariton branch. And this is interesting because at large K, it's asymptotically tending towards an excitonic dispersion. And at low K, it's got this parabolic behavior. This dispersion very much resembles that of other fluids. And the dynamics of the excitations, the polaritons, are ruled by the Gross-Pitevsky equation. So it's a type of nonlinear Schrödinger equation, which people who work with Bose-Einsteins of atoms are very familiar with. We have the kinetic energy and the density of the fluid, Gn, G being the polariton-polariton interaction constant. And we have two additional terms. One which has this gamma, which represents the losses. As I said, the photons eventually leak out of the cavity, so we have losses, radiative losses mostly. And to compensate for those losses, we have a pump. So that's just the amount of photons that we put in and the mode in which we put them in. So the Gross-Pitevsky equation is modified to become a driven-dissipative Gross-Pitevsky equation. And it describes a system which is out of thermal equilibrium. Even if the pump totally and exactly compensates for the photon losses, we are out of thermal equilibrium. We constantly have photons that come out. And these photons are precisely what enables observation of the dynamics that are happening in the cavity in the plane of the cavity. So the way the experiment runs is I have my cavity, it's cooled down, and I send a laser beam on it. I will resonantly inject photons in the cavity, and the intensity of the photons, of the laser beam that I send in, will give me the square root, the square modulus of the wave function of the polaritons. So it will give me the density of polaritons that I create. And the phase of the input beam will give me the velocity of the polaritons, or of the polariton fluid. In the detection, it's exactly the other way around. A certain amount of polaritons, a certain density of polaritons will de-excite, and that will give me an intensity that I will detect. And the fluid, which has a certain velocity profile, will give me a certain phase profile in the light that I detect at the outside of the cavity. So it's a fully optical experiment. I mean, certainly I have my sample, but besides that, all is happening optically. And for example, I can shape my beam to give a certain shape to the fluid. So here on the top, we have experimental images that we have obtained in the lab. And what I do is that I pump the fluid with a beam which is not a Gaussian beam. Instead, the mode of the beam is a Laguerre-Gauss beam of a certain degree of orbital angular momentum. And what we see here is not the beam that's coming in the cavity, that's the beam that's coming out of the cavity. Beams with Laguerre-Gauss mode are circular rings, so we get a circular ring, and if we interfere that ring with a reference beam, we get the phase of the light that comes out, so the phase of the fluid, and we see that we have circulation, rotational circulation of the fluid. So on the left, we have what I call a density map, and on the right, I have what I call a phase map, and simply in my fluid, because we want to talk about hydrodynamics, the speed of excitations is proportional to the square root of the density, whilst the velocity of the fluid is proportional to the gradient of the phase. And I can reshape the phase and the beam profile at will, just using a spatial light modulator. Again, this is all fully optical. So this looks very much like many things that people have done. Now something is a bit special. As I said, we have a driven-dissipative Gross-Pitevsky equation, driven-dissipative dynamics. So because of the interplay between the pump and the losses of the cavity, the equation of state for the polaritons depends very much on the detuning between the frequency of the polaritons, that's in green here, at every wave number, and the frequency of the pump at which I send my laser beam. So I have my laser beam, it's got a certain frequency, and these two frequencies may be slightly detuned. They may not be exactly the same for various scales. And this detuning is very important because as a function of it, I may get various regimes of density. In fact, the equation of state, which I just showed you here at the top of the screen, assumes two solutions for a certain regime of intensity of the beam. Okay, so basically, if I pump with very low intensities, the density of polaritons increases, and if I reach a certain threshold, the density of polaritons suddenly becomes nonlinear. It's got a nonlinear behavior. If I keep pumping up, I go up towards the right. But if I now come back, pump with less and less intensity, I see that I have a hysteresis cycle. And the width of that hysteresis cycles depends on the wave number, basically. But if I manage to pump on this upper branch of the B stability with a certain detuning such that it matches exactly Gn, n being the density of polaritons, I am in a regime which is analogous to what people in cold atoms know. I have something that looks like the chemical potential. At this point here, the excitations are phonons. So at this point, the fluid behaves like a superfluid. At other points, it's not quite the case. And at the moment, I appreciate that this looks a bit blurry, but we will get back to this shortly. I can just illustrate the effect of the detuning and of traveling along this branch on the excitations and on the spectrum of excitations. And this looks like this. If I'm exactly at the turning point, the dispersion relation of my fluid has this shape number 1 here on the left, bottom left. So this is very much like the shape of the dispersion relation of atomic Bose-Einstein condensates. If I pump at higher strength, or with a higher strength, or if I change a tiny bit the detuning, I see that in between the two branches of the dispersion relation, a gap opens. And that's very important. This is out of equilibrium physics. If I fall on the lower branch, anywhere on the lower branch at low density, then the two branches meet. And we even have some plateaus here. Although the interactions are very low, we have some very interesting effects there. In general, we are not going to talk much about this, but I just want to tell you that this is physical, and these are experimental data that we have recently obtained in the group, which show exactly the dispersion relation in all the three regimes that I've just presented. So we see, for example, here, at the turning point of the B stability, the very nice linear behavior at low wave number, which is a sound-like behavior. And we can even get the negative norm branch. We can get some population on the negative norm branch. So we have all the tools that we need to do some experiments on quantum field theory with this. And that's precisely what I want to tell you about. Now I want to tell you about how to create an analog of an event horizon, or an effective horizon with a polariton. So it's all the same story again. I have my waterfall with my waterfall configuration with increasing speed of the fluid and some sound waves in that fluid. And this is what it looks like. From the left to the right, the flow velocity increases, and the speed of sound is taken to be constant at the moment. And at the point at which the flow velocity exceeds the speed of sound, we get a horizon. And what I will use later is that the subsonic region I call outside, and the supersonic region I call inside. And I will refer to the horizon as an acoustic horizon, because we are talking about sound waves. And it's very simple with polaritons to create an acoustic horizon, because as I've told you earlier, the speed of sound, or the speed of excitations, is like the square root of the density. So if I have a density that decreases with space, then I have a decreasing speed of sound, whilst the phase of the fluid gives me, the derivative of the phase of the fluid gives me the speed of the fluid. So that's what I'm putting here. That's a proposal by Dmitry Solnishkov and collaborators. In black, we have the density of the fluid. So that's just like a Gaussian beam. So we see that the density decreases with x. In green, we have the speed of sound. That's the square root, roughly, of the black shape, different units. And in red, we have the phase of the fluid. And we see that just by pumping a microcavity with a Gaussian beam, just because the density dies out and the phase thus increases, we get a transsonic profile. So let's see what that tells us in terms of field theory. The dispersion in the frame of the fluid is what I have shown you earlier. What I'm going to do is that I'm going to quantize my field such that positive frequencies carry the positive norm modes, and negative frequencies in that frame carry the negative norm modes, so the A and the A dagger. And I'm going to put myself in the frame of the fluid, where the physics is stationary, and to go from the fluid frame to the lab frame, I just have a Doppler shift, so the dispersions are modified. And we see that mostly in the supersonic region, the dispersion is modified such that the negative norm branch is pulled up to positive frequencies. And this enables the coupling of modes of positive and negative norm across the horizon. So the situation is the following. In the upstream region, where I'm outside of the black hole, in the subsonic region, I have one mode that goes to the left and one mode that goes to the right. The group velocity is the gradient of the curve. And in the inside region, I have two modes that go to the right and two modes that go to the left. That's summarized in the little drawing at the very top of the screen. And basically, I have some in modes that carry the creation operator, some in modes that carry the annihilation operator. So I will have a mixing of the operators at the interface, and I will get Hawking radiation. And it looks like this. So here, what I do is that I measure the second order correlation function as a function of space. I have two detectors, and I scan them together along the x-axis. Okay, and this is what is shown here. So basically, I have my horizon somewhere around, I don't know, 12.5, no, 13 micrometers. That's the center point of the graph here. Everything that's in the bottom square, where x and x prime are lower than 13 microns, is what's happening outside of the black hole or the horizon. Everything that's for x and x prime greater than 13 micrometers is what's happening inside the horizon. And the top left and bottom right corners are where we get mixing between, or where we get correlations between inside and outside regions. And Solnishkov and collaborators made a small prediction that this white shape that we see here would be the correlations due to Hawking and its partner, the partner falling inside the horizon. And what they did not do is that they did not tell us how much the correlations are. So what I did is that I very nastily took their parameters and calculated what the correlations look like, and they look like this. So even in the 10 to the -5, the correlations are pretty invisible. And I wasn't the first to make this calculation. In fact, the first person to make this calculation was Jacopo Caruso. And his interpretation was that basically the horizon is not steep enough to get strong emission. So what he did is that he suggested that we insert something in the cavity, a defect that would change the potential of the polaritons in the horizon region in order to increase the strength of the signal. And he proposed to do that with a wire of polaritons. And we see that from the left to the right, what we are doing is that we are just changing the potential of the polaritons in the region of the horizon. And we see that the horizon can be made much steeper from the left to the right. So let's work with the right-hand side dispersion, right-hand side configuration, where the horizon is very steep. Then, this is what the correlations look like. Again, we have here in the bottom right and top left, the correlations from the from the inside and the outside of the horizon. And we see that now in the 10 to the -5, we have some trace that seems to leave the horizon at almost 90 degrees, in fact. And that extends for 25 micrometers. And we also have other traces that would be the Hawking radiation and the witness mode, and in the inner region, the witness mode and the partner. So by using a defect, as Jacopo proposed, we can increase the strength of the radiation, and we can see it. And some people have tried that in the group of Jacqueline Bloch at C2N in Paris, in the south of Paris. They tried to implement a transsonic configuration in a polariton flow. And this is what the experimental data looks like on the left. We have the density of the fluid that's shown in the top row. So they have a Gaussian-shaped beam, and they let basically the polariton fluid propagate ballistically across the defect. And we can see a cut of the intensity. So this is a real 1D propagation, and we see a cut of the density here, and we see the effect of the change of the polariton density in the horizon region. So we have something here that they say could be like a horizon. And what Jacopo did is that he did a numerical calculation of what the correlations would look like. So here again, we are in the 10 to the -5, and we get a very small trace that would correspond to the Hawking partner correlations, the Hawking mustache. It's about 10 micrometers in length, and it's, if we are very generous, 4 times 10 to the -5 in the correlations. So it's not very, very strong. And that sort of killed all the hopes that the polariton people had to ever observe Hawking radiation. And the thing is that at the time, we, I think, did not really understand well how to do the horizon correctly. So now I'm going to tell you how we can make the horizon correctly. And in fact, how this all depends on the out of equilibrium effects that, are at play in our experiment. So back to this B-stability loop. We have this hysteresis cycle here, that's due to the interplay between the pump and the losses inside the microcavity. And what I've told you earlier is that if we operate exactly at the turning point of the dB stability, then the dispersion is sonic. And if we move a tiny bit higher in density of the fluid, then the dispersion has a gap that opens. And here you see it coming. Basically, if the density in the experiment or in the simulation is a bit too high, then I have a gap that opens. If the gap opens, I reduce the amount of modes that are available to do Hawking radiation, and I reduce the intensity of my signal. Let me illustrate this. Here, I am showing you the dispersion. So in the downstream region, the fluid is propagating ballistically. You can think of it as a point of operation at the turning point. So I don't have a gap, and if the dispersion were not deformed by the Doppler effect, you would see that it's totally sonic. What do we know? We know that we will get the Hawking effect provided we get a mixing of positive and negative norm modes. So basically, at positive frequencies. So basically, we will get the Hawking effect from omega equals 0, the horizontal line here, to the turning point of this, or the inflection point of this curve, of this negative norm branch here, so up to omega max. This is the available interval of frequencies to get the Hawking effect. If in the upstream region where I am pumping and where I can be anywhere between 0.1 and 2 on the upper branch of the B-stability, if a gap opens between the positive and the negative norm branch, this gap will reduce the lower, or will increase the lower frequency of the interval, right? I have this omega mean here. On purpose here, I've shown you the data that's optimal. So we are as close as possible to 0, but we are not quite at 0. And you can imagine that this omega mean can move upwards to higher frequencies, thus reducing the interval between omega mean and omega max. That's what happened in all the configurations that we've considered so far. Basically, the density in the region outside of the horizon, in the subsonic region, was so high that we were closer to 0.2 than to 0.1. So we had a very, very small interval of frequencies because we had a very large gap between the positive and the negative norm branches. And again, this is something that's very characteristic of the out of equilibrium dynamics of our polariton fluid. So let's see what we can do with a gap that is as close as possible. And let us see how we can do it to get this small gap. And the solution the student Malo Joly found was that instead of a Gaussian profile for the pump that creates the polariton fluid, we need to use a step-like profile. Oopsie. We need to use a step-like profile. And if we have a step-like profile, you see the speed of sound here in blue, which is proportional to the square root of the density, is very, very close to the turning point. Here it's a bit exaggerated on the diagram, but it's really, really, really close as possible. In fact, I don't want to be exactly at the turning point because then any fluctuation will take me down and I will lose all interactions. I will lose the fluid. So I want to be close to the turning point, but not quite at the turning point. And I need to stop pumping the fluid a tiny bit before the defect, before the horizon, basically for ballistic reasons, for hydrodynamics reasons. You see that there is a small bump here in the density or in the speed of sound just before the horizon. And I want that bump to be as small as possible in order to stay as close as possible to the turning point. In doing so, we get a very flat profile for the speed of sound upstream. That's very close to the turning point. So we get a very large interval of frequencies over which to create our Hawking signal. So again, this is the setup. In the subsonic flow, the dispersion relation looks like this. In the supersonic flow, the dispersion relation looks like this. And then I get to calculate the correlations, the second order correlations of my field. And the way I do this is that I do a truncated Wigner approximation to numerically simulate the evolution of the field. And I do 1 billion realizations in the steady state and stationary state, sorry. And then I average to get to get my signal. This signal, compared with the signals that we have seen before, to scale, looks like this. So I like this because it gives a very nice impression of what was happening. Previously, I've shown you diagrams that went from -20 to +50 in space. Here, we go from -100 to +100. And we see the Hawking moustache, that's labeled as number 2, extend for over 100 micrometers. The correlations are in the 10 to the -3, up from 10 to the -5. So just by playing with the bistability of our fluid, by harnessing the quantum, the out of equilibrium dynamics, we've managed to enhance the Hawking effect and to bring it really to something that looks like it's experimentally feasible. Now, there is something new in this signal beyond the out of equilibrium effects that we've just harnessed. Something new is happening. And this something new are those horizontal and vertical traces here that cross at 0. So horizontal and vertical traces in correlation maps mean that we are correlating the entirety of space with something which is not moving. The fact that they cross in the horizon region means that we are correlating the entirety of space on both sides of the horizon with the horizon region. Okay, here on the top left, I am just showing you a cut of the horizontal line, just so that you see that these correlations have some structure in them, some oscillations. And in fact, the wave number or the spatial frequency that I can extract from these will be very useful in just 1 minute. So how come that we see the entirety of space on either side of the horizon be correlated with the horizon region? What happens in the horizon region? Well, for those of you who have seen other plots, like, for example, the data in Bose-Einstein experiments, you have never seen a peak like this, which is happening exactly at x = 0 in the bottom left diagram. What's happening here? Again, we go from a flow that is initially subsonic to supersonic across an obstacle. At the obstacle, the density, or the speed of sound, which is the square root of the density, is reduced. It doesn't quite fall to 0, but it's abruptly reduced. And we have continuity equations for our fluid. So because of continuity equations, because of approximative conservation of the current, this dip in the speed of sound, or in the speed of excitations in the density, is accompanied by a spike in the fluid velocity. And this is the near horizon structure that gives rise to all the phenomena that we are going to discuss just now. So at this point, when I showed this diagram to Jacopo and Luca, they told me this looks like quasi-normal mode, because I have correlations of the entirety of space with the horizon region. The best way to test this is to send a pulse on the horizon and to see what happens. So this is what I'm going to do. I'm going to send a pulse of polaritons from the left region, so from x = -50, towards x = +50, and at some point it will scatter on the horizon. And this is what it looks like. At t = 0, t running upwards, the front of the pulse arrives at x = 0. And we see that as time goes, it's partially reflected and partially transmitted. Okay, nothing new here. We have a stimulation of the Hawking effect by our pulse. What's funny, though, is that at exactly x = 0, the center of the dip, or of the peak in the fluid velocity, the density is not quite 0. In fact, it's perturbed. And we can see better in the inset here. It's perturbed and it's ringing down. Okay, it's got an oscillation frequency, and the density is decreasing, or the height of the peaks is decreasing, and it's decreasing as it's carping out two modes outside and inside the horizon. So by perturbing the horizon with my pulse, I have managed to create a coupling between this near horizon region that's inside the horizon and the outside and the inside of the horizon. So here I have some ringing that's occurring. What's interesting is that I can take a cut of the density at exactly x equals 0, and I can see the oscillations that I just told you about, and I can fit them, these oscillations, with a decreasing exponential, right? So a function that has an imaginary part. The frequency that I obtain here is exactly the frequency, the temporal frequency, omega, that corresponds to the spatial frequencies that I extracted earlier. And I will show you that just in a minute. Now, the decay rate here of this exponential is shorter than the lifetime of my polaritons. Okay, so it's a negative function, and it's shorter than the lifetime of my polaritons. So here at play, we have the decay, the radiative decay of my polaritons that is quenching the dynamics of whatever is happening at the horizon. So we have out of equilibrium physics quenching the dynamics of the perturbation. That's what gives us the ringing, the ring down. As I just said, the frequency omega that I extract here corresponds exactly to the spatial frequencies k and k prime that I extract from the correlation plot. So we have here the same phenomenon at play. The ring down of the density is the same as the correlations in the G2. So we are back to it here. What's happening? Well, as I said, we have a subsonic and a supersonic flow, and the supersonic flow velocity pulls up the negative norm branch. Okay, that's what gives me the Hawking effect. Now, near the horizon, I have a spike in the fluid velocity. So the negative norm branch is pulled up even more. And it's pulled up such that here at this new frequency, which is the frequency that I just extracted from my plots, I have negative norm modes again. So just in that region, this spike in the fluid velocity creates an effective potential, an effective trapping potential for negative norm waves. These share the same phase velocity, so they will not interfere. Instead, they will create a standing wave. And this standing wave will scatter at the horizon and outside and inside the horizon, giving rise to modes in the outside and the inside regions of my horizon. So here, this peak here is creating an effective potential just inside the horizon. And that's what gives me the quasi-normal modes. The quasi-normal modes, on this plot here, we only have the quantum fluctuations. So the quasi-normal modes, the fact that we have correlations between the horizon and the entirety of space, is entirely due to spontaneous emission. So to vacuum fluctuations that populated the quasi-normal mode. And as I said earlier, we have this very nice and long Hawking mustache, and around this long and nice Hawking mustache, we have some, well, some structure. And this structure, if we look at it very well, I don't know how well you can see that on the screen, but you can see that very much better on the archive paper for sure. This structure seems to emanate from the correlations of the quasi-normal modes with the horizon. So here we have something that looks like a modulation of the Hawking effect by the quasi-normal modes that have been excited by the vacuum. And to check this, I just do a 2D Fourier transform of the correlations that are inside this box. And I obtain, well, the 2D Fourier transform of real data. So I obtain something that's centrosymmetric. So the bottom left and the top right are exactly containing the same information. And I get something like the spectrum of Hawking radiation. And it's divided into two tones. One in blue that corresponds to Hawking and the witness mode, and one in red that corresponds to Hawking and the partner mode. This dies out, so it's a Bose distribution. It dies out in k to the -4, except that we see it better on the bottom, but it's also highlighted in red on top, except that we have a peak at some k prime or kd ku. which corresponds exactly to the omega QNM, so the frequency of the QNMs that we just extracted. So at the frequency of the QNMs, the spectrum is modulated. Where it should be dying out, we in fact have a peak. So what I'm showing you today, these are the main results really of this work, is that we have this effective potential inside the horizon that creates a standing wave, trapped modes. These trapped modes couple out to propagating waves. They form quasi-normal modes, and they are excited by the vacuum. And being excited by the vacuum, they modulate the Hawking spectrum. Okay. So this is the end of the story, or almost the end of the story. I know I'm running out of time. It's the end of the story of the paper that I wrote, but it's not quite the end of the story for me, because I don't really understand all of this. I mean, we know that the Hawking spectrum will be modulated by the gray body factor, right? We know that the quasi-normal modes, they give us the peaks of the spectrum at infinity, and we have other modes that give us the peaks of the spectrum in other places than infinities. But I don't really understand what's the link between that and QNMs, and I know that there is some literature out there on this. But what I have not found literature on, however, is the quantum fluctuations of the QNM. So I haven't found really a discussion of how the gray body factor may lead to well, the quantum excitation of QNMs. And this makes me wonder about what it means for real black holes. I mean, what's the contribution of the fluctuations of the QNMs to the entropy of the black holes? Here, what I'm doing is that I'm seeing quantum quasi-normal modes of the acoustic field. So that's like a massless scalar field on the black hole. Can this be generalized to other fields? I don't know, like the gravitational fields or Fermionic fields or whatever. I have no idea. But I hope that you may have some ideas on this. And with this, I would just like to say that initially what I want to do is an experiment. I'm an experimentalist, which is also why I don't have all the answers to all my questions. And this is preliminary data. So as I've said earlier, and many times, the speed of sound is proportional to the square root of the density. And here you see an image of a polariton wire. So it's a microcavity in which the polariton dynamics are effectively one-dimensional in space. You see that we are able to shape our beam so as to get exactly a very, very flat density and a decay in some region. So it looks like we are going to be able to implement the geometry which you see on the top left, and that we are going to be able to see the Hawking effect and possibly its modulation by the quasi-normal modes in the experiment. And that's me.
Thank you, Maxime, for the very clear and very interesting talk. A really nice result.
Thank you.